This is the beginning of theoretical probability. And this is what you think about when you think of probability. And when I say, what's the probability of rolling a 6 on a standard dice and you're yelling 1 out of 6, this is where we discover that. So there's one important tenet of theoretical probability, and that is this: all outcomes are equally likely. In other words, the dice that you roll is a fair dice, and all of the outcomes are equally likely. The probability of rolling a 1 is the same as a 2, is the same as a 3. The dice is not loaded, so that way one side turns up more than the other, okay? If you're dealing with a deck of cards, drawing a card out of the deck, every card is equally likely, okay? So this is what we're talking about the sample space. Everything is equally likely. Everything has the same chance of being selected. And so for theoretical probabilities, this is something you've already seen before. The number of outcomes in the event space, or the number of outcomes that satisfy the condition that you're experimenting for, divided by the total number of outcomes, the outcomes in the sample space. So event space are those that satisfy your condition. The sample space are all of the outcomes. So let's take a look at, again, flipping coins. And let's just start out with some very basic examples that will lead us to some rules. So let's say that you want to flip a coin 2 times. So you've got a fair coin and you're going to flip it twice, right? Heads or tails, and then flip it again, heads or tails. What are all of the possible outcomes? So we're going to let the letter H mean that you flip the heads, and the letter T mean that you flip tails. So H equals heads, T equals tails. So you could have heads, heads, or you could have heads, tails, you could have tails, heads, or tails, tails. So your sample space, the denominator in all the fractions, is going to be 4. There are 4 items in your sample space: heads, 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 tails, tails, heads, and then tails, tails. So what is the probability? And here we go. What is the probability of getting exactly 1 head? So you flip the coin two times, flip, flip, and you get exactly 1 head. Well, what outcomes meet that condition? Heads, tails, and tails, heads. Of the 4 outcomes, which satisfy the condition that they have exactly 1 head? This one does not, and this one does not. So there's only these 2. So there are 2 items that satisfy our condition of getting exactly 1 head. There are 4 total items in our sample space, and so it's 2 out of 4. 2 out of 4 reduces to 1/2, which is 0.5, which is 50%. Not too bad. Pretty easy, right? Okay, let's go to the next one. What's the probability of getting at least 1 head? So at least means 1 or more. So that could be you flip the coin and get 1 head, or maybe you get 2. So what conditions satisfy that? Heads, tails, tails, heads, heads, heads. So there are 3 items that satisfy this condition. So the fraction is going to be 3 divided by 4, which is 0.75, which is 75%. So the probability of event B, which this is event B, right? See, it's part B in the example, is greater than the probability of part A. So it's greater than the probability of part A. So that means event B is more likely to happen. If something has a higher probability, it's more likely to happen. Okay, and maybe that's kind of obvious, but we got to kind of state it. So here are a couple more. What's the probability of getting 1 head and 1 tail? Well, there are 2 items that satisfy that, so it's 2 out of 4. Done. And you can see that even though we have 50% on this, you can have 2 different events with the same event space. Okay, so this is the same as example A. What's the probability of getting a head or a tail? So you flip 2 coins. What's the probability of getting a head or a tail, that the event space has a head in it or a tail? Well, all 4 have that. And so it's 4 out of 4, or 100%. If you flip 2 coins, there is a 100% chance that you will get either a head or a tail. It's guaranteed to happen, okay? What is the probability of getting a foot? A foot, we don't have a foot. Like when you flip a coin, you either get heads or tails. And so this is called the empty set. When the condition that you're looking for cannot occur, there is no outcome that matches the condition you're looking for, it's called the empty set. And you would have 0 items in that empty set. So if you flip a coin, there is a 0% chance that you're going to get a foot. You get heads, you get tails, no foot. Okay. And then finally, what's the probability of each outcome? What is the probability of flipping a heads and heads, or a heads and tail, or a tails and heads, or a tails and tails? Remember, we said each outcome is equally likely. So they are all equal to each other, which means it's 1 out of 4 or 25% for each one. If you were to take all of these and add them up, it's 1/4 plus 1/4 plus 1/4 plus 1/4, which is 4/4, which is 100%. So if you add up all of the outcomes, this basically is the probability of the entire sample set, you will get 100% if you add them all up. So all of these examples are leading us to probability properties. So probabilities are always going to be between 0 and 1. And so 0 is, think of that as like 0%, 1 is 100%. So when you do these calculations, you will always get a number, a percent between 0 and 100%, or as a decimal, your number will always be between 0 and 1 as a decimal. If your event has a probability of 1, it is guaranteed to happen, and it's called a certain event, guaranteed to happen. If your probability has a value of 0, it's an impossible event. It will never happen. These values rarely occur. We rarely have something that is a certain event or an impossible event. Most of the time, it's somewhere in between 0 and 1. And then finally, what we talked about just a second ago, if you add them all up, remember this E-looking symbol is called sigma, and it's a Greek letter that means add them up. So if you add up all of the outcomes, all of the possible outcomes, they will equal 1. All right, so we flipped coins, we've looked at dice. Let's talk about cards and a deck of cards. Just in case you've never seen or played with a deck of cards, a standard deck of cards, here are characteristics of a deck of cards. There are 52 cards in the deck, and they're organized 2 ways. First, they're organized by suit. So there are 4 suits: spades, clubs, diamonds, and hearts. Then the cards are organized by rank, 2 through ace. Now, for our purposes in mathematics, 2 is the lowest card. 2 is the lowest card. And the ace is the highest card. There are certain card games where the ace can be actually a low card sometimes, things like blackjack. You could also play a game like euchre. In euchre, sometimes the jack is the high card and will beat an ace. That's called a bower. We're not playing those games, okay? We are just saying 2 is the low card, ace is the high card, that's it. There are also some sub-organizations going on in these cards as well. If you take a look at the 4 suits, the diamonds and the hearts are red cards, while the spades and the clubs are black cards. So even though you have 4 suits, they're actually sub-organized into red and black, okay? Also, when you look at the ranks, 2, 3, 4, 5, 6, all the way up to ace, these 3, the jack, queen, and king, are called face cards. They're called face cards because there is the face of the jack, queen, and king on the card. The other cards do not have pictures of human beings on them, right? Like a face of a human, or the jack, queen, king, right? They're just like little icons, 6, 7, 8. And so there are some subcategories going on here that you need to be aware of. But this, in general, this is our sample space. So here is the entire deck of 52 cards organized in a way that we're going to use to represent them. So we'll give the rank first, and then we'll give the suit. So this is the 2 of spades. This is the 7 of diamonds. This is the Jack of hearts. And that's the notation that we're going to use. If you're not familiar with a deck of cards, you might want to just, I don't know, pick up a 99 set deck of cards in the checkout lane at the grocery store and play around with them a little bit. Cards are interesting, and we're going to use them a lot. They are awesome for demonstrating probabilities. Okay, so let's start with this. We're going to go through a whole bunch of examples here. I apologize in advance. So here we go. Well, what's the probability of getting a spade? So how many cards satisfy our condition that they are spades? Well, here they are. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, so there's 13 cards that satisfy our condition divided by the sample space, which is all the cards of 52. So 13 over 52 is 1 out of 4, 0.25, 25%. If you reach into a deck of cards and pull one out at random, there's a 25% chance that you drew a spade. Get it? Got it. Let's go on. What's the probability that you draw a jack? So again, how many cards meet the condition that we're looking at? How many cards are jacks? Well, let's count them. 1, 2, 3, 4. There's our 4 jacks. So you take your event space, the number of items in your event space, 4, and you divide it by your sample space, 52. So what's the probability of you reaching into a deck and pulling out a card and having it be a jack? About 7.7%, about 8%. Let's keep going. What's the probability that you reach into the deck and you draw out a spade and a jack? A spade and a jack. So how many cards in the deck satisfy this condition? There's only one, the Jack of Spades. This is the only card that is both a spade and a jack. And so that means there's one item that satisfies our event space out of the 52 items in our sample space, and that is about 2%. So the probability of you reaching into a deck and pulling out a Jack of Spades is about 2%. Is it possible? Oh yeah, it's possible to do. 2%. 2% chance of having that happen. Now let's look at part D. What is the probability of getting a spade or a jack? Or a jack? Well, let's figure out, kind of piece this together. So how many spades are there? We could count all the spades, and we already did this once. We know that there's 13 spades, right? And you could show them here. Here are all the spades. And now how many jacks are there? Well, there are 4 jacks, right? We did this calculation a little bit earlier as well. There were 4 jacks. And you may be thinking, well, the answer is 17. But it's not 17. The reason it's not 17 is because we counted the Jack of Spades with the spades. And once you count something, you cannot double count it. Notice the Jack of Spades was listed once with the spades, and it's not listed again with the jacks. So when you're doing these probabilities with the or, you cannot double count a card. You can't count it twice. You either count the Jack of Spades with the spades, or you count it with the jacks, but not both. So actually, it's not 17, it's actually 16. That's the number of items that are in our event space. So our event space consists of 16 cards, not 17, 16. And the sample space is 52. So the probability of drawing a jack or a spade is about 30%. We're going to come back to this idea later on in a little bit more mathy way. Okay, so we will come back to this. What's the probability of getting a jack and an ace? So what card is both a jack and an ace? There is none. This is the empty set. One card cannot be both a jack and an ace. So that's 0 out of 52. This would be an impossible event, right? You can't pull out a card and have it be both an ace and a jack because they're two ranks, right? 2 different ranks. What is the probability of getting a jack or an ace? Well, you know that there are 4 jacks. You know that there are 4 aces. None of the cards are double counted, so we don't have to worry about that. So it's just going to be 8 out of 52. And then finally, what is the probability of getting an ace? 4 out of 52, 7%. Pretty easy. Now let's ask a different type of question. And this is off of G. What is the probability of getting an ace? 4 out of 52. What is the probability of not getting an ace? So this idea of not getting an ace, we could do this two ways. Method number one, let's count all the cards that are not aces, right? Because that's what we're looking for. We want the probability of not drawing an ace. So let's count them. Okay, here we go. 1, 2, 3, 4. Oh, this is taking a long time. 5, 6, 7, 8. So you can see it's going to take a long time to count these all up. 12 out of 13 is equal to 48 over 52. Here's your percentage, 92.3%. But it takes you a long time to count how many satisfy your condition of not being an ace. Instead, we could do something called a complement. And here's the idea of a complement. If I tell you that there's a 30% chance of snow, what is the percent chance of it not snowing? And you can do this in your head, right? That means there's a 70% chance of not snowing. These two are complements of each other, and they always add up to 1. So the probability of it snowing plus the probability of it not snowing equals 1. So if we wanted to know the probability of it not snowing, what we could do is say 1 minus the probability of it snowing. Or I should say 100%. Maybe I'll do that. 100% minus 30% is the 70% of it not snowing. This is called the complement. And this is the idea that we illustrate here. So if you take the probability of drawing an ace and the probability of not drawing an ace and add those together, you get the number 1. And here's the idea graphically. So this would be the probability of drawing an ace, the probability of getting an ace. All this here is the probability of not drawing an ace. That's called the complement. And if you add them together, you get 100%. You get the whole. We can use a little algebra and move this around and say, okay, if we start with the 100% and we subtract the complement, let's say 30% chance of snow, then we know that there's a 70% chance of it not snowing. And so if we go back up here, what we could do is we could say that the probability of not getting an ace is 1 minus the probability of drawing an ace. And we knew the probability of drawing an ace was 4 out of 52. So that would be 4 out of 52. Now this is going to be 52 over 52. So that's just going to be 48 out of 52. And it took us a lot less time to count 4 items than it would to count 48 items. So this idea of a complement is going to come into play in just a little bit. So here's some more examples of complements. So suppose that it's raining today. The probability of it raining is 45%. What's the probability of it not raining? 1 minus the 45%, right? So 55%, okay? The probability of not getting the flu is 0.24, 24%. So what's the probability of getting the flu? 1 minus 0.24, which means there's 76% chance of getting the flu. Okay, so hopefully this complement idea, it's a way of making the mathematics a little simpler so you don't deal with such large numbers. And so here you go. We're looking for the probability of not drawing a queen. So what you can do is first find the probability of drawing a queen and then subtract that number. That's 4 out of 52. Subtract that number from 1, and that will give you the probability of not drawing a queen. So the probability that you reach into the deck, pull out a card, and it's not a queen is 92.3%. And this takes us right up to events that are mutually exclusive. So mutually exclusive, exclusive means that you don't share anything. You're exclusive to a certain set. And when you're mutually exclusive, that means neither of the events share any outcomes between the two of them. And so in this situation, we are looking at 2 mutually exclusive events or outcomes. So the first one is, what's the probability of drawing an ace. And you see that the aces are this yellow circle, and all the aces are contained within the yellow circle. This is kind of like a Venn diagram. And then you have the probability of drawing a queen. And again, here's the probability of drawing a queen, and the queens are all together in their circle, and there are no cards that are shared between the two circles. There's no cards that are shared between the two outcomes. They are mutually exclusive. Now, what we want to do with these two mutually exclusive events is we want to AND them, and then we want to OR them. So we're going to put them together, first with and then with OR. So let's start with the AND. So if you take a look at this and you say, okay, what is the probability that a card is an ace and a queen? So you reach in the deck, you pull out a single card, and that card is both an ace and a queen. There is no card that is both an ace and a queen. Like the top half is an ace and the bottom half is a queen. I don't know. No, we don't have cards like that, right? And so this is the empty set. 0, 0. That is the probability of this happening. They are mutually exclusive. There are no cards that they share. There are no outcomes that are shared between these two sets. So the AND of a mutually exclusive is just 0. Now let's talk about the OR. So the probability of getting an ace is going to be, and I'll write this out, 4 out of 52. And the probability of getting a queen is also 4 out of 52. So the probability of reaching into a deck and pulling out an ace or a queen is 8 out of 52, which is 15.4%. So when you have two events that are mutually exclusive, the AND operation is 0. They don't share any common outcomes. And so the AND operation of the two are 0. The OR operation, you just add the two probabilities together. Pretty easy. You just add them together. Piece of cake, right? All right, now let's look at the situation where two events are not mutually exclusive. So when we say not mutually exclusive, that means there is a card, there is an outcome that is shared between the two sets. So in this situation, the yellow set is the probability of drawing an ace. And you notice that there are 4 aces, right? 1, 2, 3, 4, right here. And then the blue is the probability of drawing a spade. And here are the 13 spades. They're represented right here. And you may notice that there is an overlap. There is a point or an outcome that is both in the yellow and in the blue. There is a card that is both an ace and also a spade. It happens to be the ace of spades. There is a card that is both yellow and blue. That's the green ace of spades. See what we did there? Yellow and blue make green. Get it? See, together, same. Okay. So the colors matter a little bit in this one. So let's look at, again, the AND and the OR. So we want to take these two non-mutually exclusive events and put them together. So let's put them together with the AND. So we're looking for things that are in set A and in set S that are aces and spades. And we've already identified that is the ace of spades. There is one card that is in the AND region, that is in the overlap region, that is member of both sets. And so the probability of you drawing that card that is both an ace and a spade is 1 out of 52, 1.9%. Piece of cake, done, got it. Now the tricky part, and you've already seen this tricky part, okay? So this should jog a memory. What about the OR? What about the OR? Now, remember, flashback, the last time we did the OR up here, you just found the probability of set A and you added it to the probability of set S and this, or Q for the queen. And we just added them together, right? You found the probability of set 1, the probability of set 2, you added them together and you were done. Well, that will cause trouble here when you have non-mutually exclusive. And let me show you why. So we're going to start with the probability of A. So if you take a look at what is the probability of drawing an ace, you would say it's 4 out of 52 because there's 4 of these, 1, 2, 3, 4. And then if you said, what's the probability of drawing a spade? there are 13 spades, right? So that'd be 13 out of 52. And you may be thinking, oh, well, I'm done. I just take 4 and I add the 13 and I'm done. And it should be 17 out of 52. But you counted the ace of spades twice. You counted it once with the aces and you counted it once with the spades. And you can't do that. That's an illegal move. You can only count the ace of spades one time. And so what you have to do is subtract the double count. You have to subtract the number of items that are in the and, which is what we calculated up here. See that? There's the and component. And so you take the probability of an ace plus the probability of a spade minus the probability that it's an ace and a spade. The probability that it's ace and spade is the green region. That's the double count, and you've got to subtract that. So it actually shakes out to be 4 over 52 plus 13 over 52 minus 1 out of 52. And that is going to leave you with 16 out of 52. And if you do 16 out of 52, you'll get 30.8%. This is tricky, and you got to watch for this. When you have two sets that are not mutually exclusive, they share certain outcomes, you always have to subtract the double count. These are the rules, by the way, without all the pictures and explanation, just like, boop, here are the rules. And then we walk through and we do a couple examples here where we just look to see if things are mutually exclusive. And so we could go down here like, let's take a look at this one. What is the probability of getting a sum of 5, or the first die being a 2? So what we're doing here is we're rolling 2 dice. And if you want to look at the sample set for this example, here's the sample space when you're rolling 2 dice. So there are 6 outcomes this way, and there are 6 outcomes this way for a total of 36 outcomes. Okay, so if you're rolling 2 dice, 2 6-sided dice, you could roll a 1-1, a 1-2, a 1-3, a 1-4, 1-5, 1-6. Or you could roll a 4-1, a 4-2, a 4-3, a 4-4, 4-5, 4-6. Okay, get it? So they're all listed here. The first die is the first number, beep, beep, the 1, and the second die is the second number. So you're rolling 2 dice simultaneously. And what we'd like to know is, what is the probability, going down here, of getting a sum of 5 or the first die being a 2? Okay, so let's go up and look at this. So if we go up here, remember A, the probability of A was that you had a sum of 5, and the probability of B was the first digit was a 2. So I'm going to write it like this. 2 was the first digit, and then we got some number in here for the second digit, okay? So I actually want to write this in a different color. Let me write this in green. So P of B is 2 comma some number. So what's the probability of A? What's the probability of getting a sum of 5? Well, let me count how many there are. 1, 2, 3, 4. There are 4 dice rolls that have a sum of 5. You may notice, because of the orientation of this, that these are kind of on a diagonal, almost like a word search, right? Where you're looking for the letters that make up the word. So you'll see that these are on a diagonal. So the probability of rolling 2 dice and getting a sum of 5 is going to be 4 out of 36. 4 items meet the condition that they have a sum of 5 out of a total of 36 outcomes, right? Okay, now let's do the second part. What is the probability that they start with a 2? Okay, so here's a 2, 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 here's a 2. So how many are there? 1, 2, 3, 4, 5, 6. So there are 6 outcomes that satisfy this condition. So I've got 4 out of 36, which is the probability of A happening, rolling, getting a sum of 5. And I have 6 out of 36, which is the probability of B happening, that the first digit is a 2. Now, are they mutually exclusive? They are not mutually exclusive because they actually share this number. The roll 2, 3, 2 comma 3 is both in set A and in set B. So just be aware of that for right now. So if we OR these, what was the probability that we had a sum of 5? That probability was 4 out of 36. Plus, what's the probability that the first die is a 2? That was 6 out of 36. Minus the overlap. How many items were in both? 1 item was in both. 1 out of 36. And you'll see these numbers are all written right down here. Boop, 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 boop. And when you take 4 plus 6 minus 1, you get 9 out of 36. So the probability of rolling 2 dice and getting a sum of 5 or the first die being a 2 is 9 out of 36. Punch that in your calculator, boop, 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 and you get 0.25, 25%.